So let's just talk about the reason why Kc, the equilibrium constant, has no dimensions. We know that Kc, we typically write it with concentrations and of reactants over the products, and then depending what the stoichiometry is, gives you the power at which each one of those are either squared or to the power 3. What we're actually using is, instead of the concentrations, we're actually calculating using what's called the activity of a substance. And the activity of a substance is a measure of its effective concentration under these specific conditions. And so what we're basically saying is that for relatively dilute solutions, a substance activity and its concentration are roughly equal. And that's typically what we're working with. Typically working with relatively dilute to very dilute concentrations. If we're talking about things that are extremely concentrated in a solution, this begins to deviate from what Kc is. Now, the most important thing to realize is that the activities for pure solids and liquids are equal to 0. So this is the most important thing to realize, is that activity for solids and liquids equals 1. So this reason is QC and KC expressions do not contain terms for solids or liquids. So let's just look at a couple of examples of this. If we look at, as an example here, this is lead chloride, which is in equilibrium with lead 2 plus and chloride ions. If we were to write the equilibrium constant, we of course are looking at these two here, so this would be the concentration of lead 2 plus times chloride ion, and then of course there's going to be a 2 here because of this 2, and then it's going to be divided by this concentration or activity. Now, because this is a solid, the activity equals 1, so this is going to be over 1. So the value of Kc, which is also the value of Qc, remember, is just going to be equal to lead 2 plus chloride minus to the power 2. So important to realize that any time we have a solid or a liquid, this is going to be the case. So here, for example, let's just have a look at this one. So QC, which of course is going to equal KC, is going to equal QC, but the concentration here, or the activity of this term, which is going to be on the top, is just going to be 1. And then underneath there's carbon dioxide, which is a gas, which is the concentration, but this term here is also a solid, so it has a activity of 1, so this would effectively be times 1. So in this particular case, Kc equals 1 over the concentration of CO2. Because CO2, calcium oxide and calcium carbonate are both solids, they're not going to influence the reaction quotient or the equilibrium constant. And so we could just look at one more here. Here we've got a solid. These two are gases. So we can say, well, CS2 is going to be divided by the concentration of sulfur squared, but this activity is going to equal 1, so it doesn't appear in the expression. And so the last one we could do is look at this one here. We would realize that Kc is going to equal the concentration of bromine gas, which is going to be on the top, and then it's going to be divided by, well, This is a liquid, so it's going to, the activity is going to equal 1, so it's going to be the concentration of bromine gas over 1, which is going to be related to the concentration of bromine gas. And so this is why we talk about Kc and Qc being dimensionless. And the most important thing to realize is that the activity, which is similar to concentration for solids, is going to equal 1. For liquids, it's going to equal 1. So this is the most important thing to take away from that.